Yesterday we were visiting the Dutch's palace, and Venice was the center of the world. Well, we in Örebro like to think that Örebro is the center of the world, and illustrating that we are at least in the middle of Sweden. Our lab has been working with pop analysis. We've established for 10 years ago, doing everything from dioxins to the new pops, brominated flame retardants and fluor compounds. And this is an illustration of some of the work that we're doing in our lab. But today I will talk a little bit about the UNEP project, and Heidi has already touched upon a little bit on UNEP in this morning. So what's going on is that all the countries that signed the Stockholm Convention have to, at one time or another, submit data to the Global Monitoring Program. And what the Global Monitoring Program wants to achieve is that we were able to detect a decline in levels, hopefully a decline in levels, within a 10-year period. Now, when you translate that to analytical quality or analytical variance of your data, then the analytical variance between laboratories has to be below 20%. And we all work in this quality assurance studies. This is quite a challenge, and I will show this is quite a challenge for laboratories in Europe, US, and the developed world. That's certainly a challenge in the developing countries. So I'll talk a little bit about the challenge that we want to achieve and the first results of the first quality assurance control that we conducted together with under UNEP flag. Well, how did we start? We started with a quality control. How do we quality control all the laboratories that signed up for the UNEP database? UNEP and especially Dr. Fiedler has been working on a database of all laboratories doing pop analysis, and many laboratories and many countries submitted laboratories in the database. But how do we check the performance of these laboratories? Because if you send in a form, you suddenly say, well, we can do this, we can achieve this LODs, and we are doing this and this analysis, but how can we prove or how can we see that in reality that's true? Now, I've been, and many of you know, I've been involved in these QA/QC studies, and I'm very much in favor of sending these blind samples to laboratories. And okay, you can do whatever method you want to use, but prove that you can do this analysis. So we are very much in favor of this proficiency testing, sending blind samples to the laboratories or standard solutions, and use your own technology. So we were not limited to technology, but show that the numbers are right and we control them. We've been doing that for the last 15, or this is an old slide, I think it's already nearly 20 years, different kind of studies. If I started 1992 in Umeo, I think we're now doing this for more than 20 years. A couple of years ago, we combined all these results that we've been achieving throughout the last 20 years, and we came up, we have more than 100,000 data points of different laboratories from 1992 to 2012. We've reviewed that in a paper for analytical chemistry, and just to show a little bit on the results is what can we achieve in terms of RSD, of variation between the laboratories for in this case dioxin analysis. And if you can see, it's for incineration related samples, we're down to an RSD, well, a little bit below 20%. If we look at sediments, we're doing a little bit better, 15%. Extracts, you don't have to do the extraction stage, we're down to 15%. Standard solutions, routinely, we can be under 10%. So, in view of these goals that we could have for the Stockholm Convention, it might be achievable, but still it's a challenge, but it might be achievable. Theoretically, this is a graph I stole from Gauthier Épée from the Liège, the Liège University, where we look at the theoretically Horowitz equation, where you can see when you go from 1 gram to down the detection limits that we want to achieve, and you can see the variance in the data. Now, the Horowitz equation was designed in the 1980s, and Gauthier Épée has designed the extended or the adapted Horowitz equation Now we can see we are in this area, and we should be able, theoretically, be able to achieve this below 20% of variation. So both theoretically and practically, we are about in the same, you can say in the same ballpark that we want to achieve for the UNEP study, and that we have to achieve if we want to submit data for the global monitoring program. So we started out with dividing the world in 3 regions, Asia, South America, Middle America, and Africa. And both at the same time that we were organizing this study, we did certain training, capacity building efforts in both Africa and South America, and we were, especially our group was very active in Asia. After this capacity building, helping people on get started with the analysis, or in some way achieving or helping them out in the quality of their work, we were selecting some 4 different sample matrices that we want to check for the quality assurance study. Human milk, which is one of the matrices that UNEP has chosen as the key matrix that we're going to do. Sediments, because we think, although it's not chosen as the main focus of the global monitoring program, many people do sediments and fish samples. And then fly ash, because at that time we were thinking that this would be a substitute for air samples. Of course, it's not really the same, and some of the compounds are missing, but fly ash, it's mostly incineration related and air related. So we added that to the study. All the compounds, what you would say the old Stockholm Convention compounds in 2009, brominated flame retardants and persistent fluor compounds were added. All the old ones, including dioxins like PCBs, marker PCBs, the drinks, chlordanes, DDTs, hexachlorobenzene, Mirex. And we were also thinking of including toxaphene, which is on the Stockholm Convention, but there were nearly no laboratories doing toxaphene analysis, even in Europe and US, but even in developing countries there was no laboratory with capacity on toxaphene. So for the time being, we excluded toxaphene from our study. Problems? Well, I've been organizing these studies for many years, and it always went relatively okay. I know what paperwork to fill in, but when you start sending things to Africa and South America, it's a whole new world, which is a whole new administrative world, which is opening for me. And some of the samples, and especially the milk sample, that we want to have quick response times, it was difficult to sometimes get it through customs or to get it in place at the time. We have certain samples we had to send 3 times, and the 3rd time it arrived on time at locations. Some problems, I thought, if you put the UNEP label on it, it would go quicker. I think that's a complete misconception. I think if people see the UNEP label, they think, whoa, here is money to be made, and they keep it at customs, and they want the labs to pay to get it out, because they think the UNEP will pay everything for them. But at least we get, I think, nearly all the samples. Some of the labs were excluded because the milk sample was arriving too late, and we didn't advise them to analyze it. So some of the labs didn't report for milk because of this customs problems or late arrival of samples. But most of the stuff we got at the sites where we wanted it. In total, we had a little bit more than 100 shipments made to Asia, South America, and Africa. Like I said, for me, looking at this quality assurance thing, it's not important what kind of method you are using, and we advise people to use their own method in their own laboratory, what they're able to achieve. Use in-house method, because especially in developing countries, some things are a little bit different than in our Western world. We had some UNEP training, like I said, in some of the laboratories, and we'll see if they was this beneficial and was their level raised because of our training. Also, we used their own standard solutions, but many of the calibration standards that we saw in the laboratories when doing the training or inspection tours before were of poor quality. So UNEP, we did some effort to sending calibration standards to the different laboratories. A large part of, or some part of the budget went to get correct standards to the different laboratories with help of CIL, Ben, and help of Wellington, the two suppliers of the two main suppliers of internal standards. We also wanted to check the laboratories to check the blanks. Did they run certified reference materials or QA/QC charge? Now that's routinely in our laboratories, but there's still a long way from happening in developing countries. We talked a little bit about criteria. We wanted to look at recovery. We wanted to look at signal to noise, if they have values or LOD values. And again, I think that Esteban Abad also touched upon that. We wanted to look at the difference between upper bound and lower bound. But that also was, it's a difficult criteria, especially if you, in some of the samples, if you don't find anything, or if there's nothing present in some of the samples. Now, the samples that we had selected had very high levels of the target compounds. So it shouldn't be an issue in this case. We're looking at individual congeners, and we're looking at the TEQ. Report forms look like this. We'll ask for the levels of the different compounds. Some confusion because some of the samples were very high concentration, and the number in nanograms per kilogram becomes very large. And some of the laboratories, they changed it themselves, and there was some confusion about the units, and we tried to facilitate that as much as possible, but some of the results might be still contain this mistake in units, and the laboratories were not so used to this kind of studies, and normally you can react and you can change if there's a mistake in the units that you report, but for many didn't report back to us when we say, please look at your numbers once more if this is a factor of 1,000 or if something's wrong, and they didn't report back to us, and then we had to keep the probably wrong values. We want to also look at which kind of methodology people were using, which kind of instruments is especially interesting to see from high resolution to GC-MS/MS to GC single quadrupole to GC-ECD, and how that would reflect the results. We're looking a little bit at statistics. We use Cofino Statistics, which is normally used in the quasi-MEM program. I did myself some calculations and looked at the normal statistics that we use in the Intercal program, or the same statistics that we're using for the SINT, which study which will be presented tomorrow by Stefano. And actually it is only the average value, the mean value that we're interested in, because UNEP has set this RSD to 12.5%. So we're only interested in the mean values, and the mean values, if you use the Cofino statistics, the statistics from that we are using in Intercal and the ones that we're using in the SINT, they're very close. They are less than 1% of difference. So the whole difference in the validation of set scores, the difference are very, very little, except for some special cases. So the criteria was set to 12.5%, and if you already understand now, if you have 12.5% of your RSD, this is a very tough criteria for many laboratories to achieve. Now let's look at some of the results. Different areas. We look at Africa here, and here we're looking for the twins in a standard solution. Here are the results for Africa, the results for Asia. Now, if we talk about Asia, then it's 90% or 95%. It's coming from China. The results come from China and Japan. So very advanced instrumentation, and many of them are using high resolution instrumentation. The Central European countries, here two participants, GRULAC, which is South America, and the Caribbean countries, which are here, and the rest of the world, or the rest of Europe, and US laboratories here. So we're looking at them in regions. For standard solution, well, the results are not too bad. If you look at the number of laboratories within 2 standard deviations, which is the criteria which they would be allowed to participate, would be allowed to submit data to the global monitoring program. But if we look at the real sample, DDT in the sediment, we see some problems in the GRULAC region. And like I said before, I suspect that some of the low numbers are just reporting the wrong units in our study, despite that we've asked to check the results once more. Marker PCBs, again, for the standard solutions, we're doing okay, except for 2 laboratories in China, which were deviating from the mean value. But most of the laboratories qualify for a standard solution. But again, if you look at the real sediments, there are, and if you're using this strict criteria, many laboratories fall outside 2 times the standard deviation, and their results can be assigned as questionable. Dioxins for the standard, and if we look at the TEQ basis, we're doing quite okay for many of the laboratories. Again, dominated by Asia, by laboratories in China and Japan, which have high resolution capacity. And what you also can see is that in Africa there's only 1 laboratory doing dioxin analysis, and in Central Asia, Central and Eastern Europe, there are 3 laboratories, and also in the GRULAC there are not so many doing dioxin analysis, but there is some capacity, and they perform relatively well on standard solutions. But if we look at one of the key matrices, and Dr. Fiedler also came back to that a little bit before. That's one of the reasons why the milk samples are sent to the European Reference Laboratory, because if you look at the capacity, there's only capacity in China, 1 laboratory in Egypt, and 1 laboratory in Central and Eastern Europe, and the rest of the world. But there's very little capacity for milk, which is one of the key monitoring matrices for the GMP. So we have some work to do before things are satisfactory. Also, an overview that Heidi also showed this morning. The strange thing from that is that for dioxin results, the satisfactory results with a Z-score between minus and +2 are very acceptable, and that's because most of the laboratories that were working with us were having high-res capability and were very well equipped. Now, these same laboratories then try to do the other POPs in milk and in PCBs and other POPs, which they don't do routinely, and then the results were much worse in some cases, and only the qualification for fish is with high levels of DDT or PCBs, then only less than 40% of the participants of the 100 laboratories that we selected were showing satisfactory results. Look a little per region. We've checked different regions. Again, on an individual basis for PCBs. But one of the interesting things is to look at and that's also reflected in the TEQ value. If you look at the different isomers, they're all over the place. But if you look at the TEQ, which is a weighted average, it can be in one dioxin a little bit too low, another one too high. Suddenly, if you take the average, and I will talk about also with the chiral focusing, if you take the average and if they have the same toxic equivalence, well, there's no problem with achieving very good results with the TEQ value that's normally reported. Same is true for fish samples, but then the variation is much too high for what we think is too high. It's the RSD is about 50%, and we want to achieve much lower numbers. Some conclusions. Well, there is capacity available both in Western Europe and the rest of the world, but still there are some problems. There are large differences between areas that we assigned within the UNEP. Asia is a problem, or is not a problem, but developing Asia is a problem, and Asia is dominated by China, Japan, Korea, and Taiwan, which have had dioxin capacity for a long time. For some reasons, there are some problems with POP capacity in the pesticide because the laboratories are mainly focused on dioxins. GRULAC, a lot of pesticide capacity, much more than dioxins, especially in South America. In the Caribbean countries, still a lot of problems with the analysis, where we did extensive training. Esteban Abad was in Cuba, extensive training, and still not satisfactory results from most of the laboratories from Cuba. and limited capacity for dioxin-like POPs. Africa, very limited capacity. One laboratory we could find in Egypt which performed relatively well, and now with the resolution we lost contact with the people that we work with. So the only laboratory in Egypt which was working is now we lost a little bit of contact with them. There's one bioassay laboratory in South Africa. So there's very limited capacity for dioxin-like POPs, and there's, well, also I would like to say, I think I should say, very limited capacity for pesticides. Normally they can do one DDE or one DDT, maybe some PCBs on the ECD, but the capacity is still very limited in Africa. Conclusions for the matrices. Mother's milk, still a big problem. So UNEP and Dr. Fiedler has solved that another way. And also air, the matrix which we do a lot of the passive samplers, and like the data showed this morning, we do that a lot in reference laboratories, and we and Esteban and Jacob de Poer's lab at IBM has done a lot of work there. There's some capacity, more interest and capacity, and that's also this morning. People are interested in food, fish. They do a lot of fish samples and also sediments. They are much better equipped for fish and sediments. With that, yeah, future activities. We are planning a second round of this UNEP intercalibration study. We will have the call out in 2011, probably, hopefully before summer, but 2012 it is. It's good that you noticed that. The shipment will be in 2012, hopefully the end of 2012, beginning of 2013. We will focus on some of the new compounds on the Stockholm Convention. The brominate flame retardants will be included, and PFOS and PFUA, the persistent fluor compounds. And we're discussing a little bit synchronization with Intercal, with SYNT, and with the food intercalibration, that we don't do the same things at the same time. So we try to synchronize that you don't get the same samples in your lab in the same year. And we would like to have more people from Europe and from the developing countries to participate in this study, to get, that gives us better averages, and this gives us a better study to do on this. And I would like to stop and acknowledge the many people who've been involved in this very big project, but very nice, very promising results, but still we have a long way to go in this project. Thank you.
Thanks, Bert. Thanks very much for that. Is there any questions for Bert?
Yeah.
Do we have a mic?
We have a mic. Can I blast it out?
Yeah, go ahead, Jack.
Okay.
You're okay.
I guess I noticed you were looking at GC columns. I assume that you tried to at least apply some reasoning on selectivity differences that might occur between labs. And the one I think about is the marker PCB 138, where you have 163 in Paracore 1254, 1260, and 50% of the concentration approximately at 138. And most columns out there don't separate 138 and 163, but there are a few. What do you do when you get somebody that's using one that does, and all the answers are based on what I would consider potentially to be erroneous?
Yeah. Now, yeah, what you see, and still there's a lot of data out there. I totally agree that people reporting 138, which is the convolution of 138, 164. So it is a problem. We used a 60-meter column, but it's difficult still to separate them and to get people into a routine that they say, well, this is 138, but they say, well, but I have to have a time trend, and 5 years ago I do this, so they keep the same. So this is an issue, and you can actually see it in the data, that you can see a grouping of two groups of laboratories, ones which separate 138 and ones we don't. And that's why we use a little bit this Cofino Statistics, which is a little bit more advanced, which try to handle, which can show that there are two different populations of results. But it's a problem, yes, definitely.
Thank you, Bert.